Another way to describe data is by the spread among the data points within a data set. So, how can we measure this spread? We can measure the range of the data points. Consider the data shown in figure 2.4 on cholesterol measurements on a given person by two measurement methods. It is obvious from the illustration that the values that the auto-analyzer method gave are more spread apart than those of the microenzymatic method. In other words, it has a greater range. The range is the distance between the largest and the smallest values of a data set. Although the sample mean in both cholesterol measurement methods are the same, 200 milligrams per deciliter, we may conclude that the auto-analyzer method is less precise than the microenzymatic method. Here are other things to consider about the range. Another measure of data point spread is a quantile. Quantiles may come in different scales, deciles, quartiles, or percentiles. Let's focus on one of them, the percentiles, as the principle of obtaining them are the same. The pth percentile is the value v sub p, such that p% of the sample points are less than or equal to v sub p. For example, 30% of the sample points are therefore less than or equal to the 30th percentile of a data set. Here are more specific definitions of the pth percentile. We are going to go through these on the next couple of slides. The k+1 largest sample point, if n times p over 100 is not an integer, where k is the largest integer less than np over 100. The average of the np over 100th and np over 100 plus 1th largest observations if np over 100 is an integer. We go back to our data set on the 20 birth weights of infants from an hospital. We are going to find the 10th and 90th percentiles of this data set. First, we arrange the data points on an array from least to greatest. We then compute for the NP over 100 for the 10th and 90th percentiles. So our N here is 20, number of samples. In the case of 10th percentile, our P over 100 is 10 over 100 or 0.1. 20 times 0.1 is 2, which is an integer. The same is true for the 90th percentile. The results show us that the NP over 100 of both percentiles are integers or are non-decimals. For the 10th percentile, NP over 100 equals 2, or the second data point on the array. Therefore, the 10th percentile is the average of this second data point, which is 2,581, and the next data point, or 2,759. The same is true for the 90th percentile. Now that we know the 10th and 90th percentiles of the birth weight data set, we can then say that we would be able to estimate that 80% of birth weights will fall between 2,670 grams and 3,629 grams, which gives an overall impression of the spread of the distribution. Although quantiles require a little bit more steps to obtain, they have an advantage over the range. They are less sensitive to outliers and to the sample size n. Let's go back to this chart of the comparison of spread between two data sets. The cholesterol measurements obtained using an autoanalyzer method and those obtained using microenzymatic method. How else might we quantify the spread of data points shown here, aside from using the range or quantiles? How about we add up the distances that each of the data points are from the mean? Here's how it would look like for the autoanalyzer data set. So in this case, we subtract the mean 200 from 177 to give us negative 23. And we do the same for the data points 193 and 195. And for the data points to the right of the mean, we subtract the mean from the data points, giving us positive numbers. 209 is 9, and for 226, that's 26. How about we add up the distances that each of the data points are from the mean? Here's how it would look like for the autoanalyzer data set. Let's see if this will give us some meaningful numbers. The sum of the deviations of the individual observations of a sample about the sample mean is always 0. So that's a problem. We didn't get any meaningful spread because the answer is 0. In order to avoid adding the deviations up to 0, we may consider using absolute values for the sums and differences of the distances between the data points and the mean. We call this the mean deviation, but it's not quite the best expression of how spread the data points really are. Why? Using the absolute values of the distances of the data points from the mean is not enough to represent the magnitude of the distances or spread. A better way to achieve this emphasis on the spread is to square the distances instead. Thus, we arrive with a formula for variance. To calculate sample variances, or S-squared, that are unbiased, we need to change the numerator n to n minus 1 in the formula. Square rooting the sample variance gives us the sample standard deviation, or S. So the question is, why should we change n to n minus 1? we need to consider the number of values in the final calculations of the statistic that are free to vary. We call this the degree of freedom. If you have any questions or clarifications as to why we should consider having degrees of freedom for sample statistic calculations, fire them up during our next video teleconference. So there you go. The different tools for descriptive statistics are indeed things that we've heard about since our grade school days. I'll leave a bit for you to read about. The coefficient of variation. In the next lessons, we will tackle how ungrouped data may be grouped and represented in charts and graphs to make them even more informative and attractive to the target audience.